Breaking news seldom arrives gently from the outer dark. In the cold gulf between Mars and Jupiter, a stranger is brightening as if waking from an ancient sleep. Astronomers call it 3I/Atlas, 3I, for the third confirmed interstellar visitor ever seen by human eyes. And in mid-September 2025 its light curve began to rise in a way that models did not anticipate. The numbers, indifferent to hope or fear, revealed a blunt truth. An object forecast to hover around magnitude 15 or 16 surged toward 12 to 14. A leap that, in the inverted logic of astronomical magnitudes, means multiple times more light pouring into our telescopes. Magnitudes run backward. Lower is brighter. 2 steps down is roughly 6 times the glow. But this was not a gentle glide. It was acceleration, data points climbing above the tidy slopes that textbooks prefer. Inside roughly 2 astronomical units from the Sun, the distance marker at which many comets only begin to stir, something changed. 1 AU is the Earth-Sun span, about 93 million miles. 3I/Atlas, still twice that far from our star, behaved as though it had crossed an invisible threshold. The most cautious explanation reaches for the physics of ices. Carbon dioxide, water, and more exotic volatiles, trapped since formation around a different star, suddenly sublimating as sunlight grows harsher. In vacuum, these materials do not melt. They skip the liquid state, exploding straight from solid to vapor. Gas drags dust and grit with it, inflates a tenuous atmosphere. The coma, that catches sunlight and throws it back. Yet rapid brightening is a double-edged omen. It can signal life and instability in the same breath. Outbursts that fracture a nucleus into shards, fountains that blaze and then fade as volatile stores are spent. 3I/Atlas, outpacing the curves, implies processes that our solar system habits only half prepare us to recognize. No one is ringing planetary defense alarms. The ephemerides are firm. It keeps a respectful distance, never much nearer than 1.8 AU from Earth, a safe span by any measure. The alarm, such as it is, concerns comprehension. For the first time in its existence, this object, a time capsule forged in a protoplanetary disk that never knew our sun's warmth, has entered the inner heliosphere. Chemistry that slept for eons in the interstellar night is being heated into speech. Exotic ices stable in the deep cold may be sublimating for the first time since birth, releasing gases that sketch fingerprints from another system across the blackboard of space. Dates sharpen the sense of a clock we did not wind. October 3rd brings the closest pass to Mars, a mere 30 million kilometers, close enough for orbiters circling the red planet to attempt what Earth's telescopes may soon be unable to do. By late October, around the 29th to 30th, perihelion arrives at roughly 1.36 to 1.4 AU. And then nature plays its oldest trick on observers bound to a sunlit world: geometry. In early October through early November, 3I/Atlas slips into superior conjunction. From Earth, the comet huddles near the sun's glare. The sky is too bright, the angle too small. The floodlight washes out the firefly. The peak of activity, when heating is fiercest, jets most violent, and chemistry most revealing, occurs behind the curtain. We will lean on mechanical eyes scattered across the solar system. If fortune holds, Mars-based spacecraft, and later the watchful sentinels orbiting Earth's night, will help. But the brightening trend suggests a temperament unwilling to pass quietly through perihelion. An energized coma, perhaps building toward episodic outbursts, could expose structure, rotation, and composition that otherwise remain hidden in a faint blur. The riddle is whether revelation will coincide with the weeks when our largest mirrors are blind. What then are we looking at? Not only a comet by habit, and certainly not an asteroid by restraint. 3I places it in a lineage of exactly 2 prior interstellar visitors. 1I/Oumuamua in 2017, enigmatic, dry, accelerating for reasons still debated, and 2I/Borisov in 2019, decidedly comet-like but chemically unlike our native swarm. Each broke a rule. Each wrote a new one. 3I/Atlas continues the pattern. A swollen atmosphere measured at scales that challenge experience, a brightness rise ahead of expectation, and whispers of colors and geometries that hint at alien chemistry. Each interstellar body arrives with its own constitution and its own instructions for how to behave under a sun it did not evolve to endure. Imagine its history. A seed pebble in a foreign nursery of dust and gas, circling a star whose light had a different hue. Its ices condensed where carbon dioxide could freeze with ease, where water's story may have been scarce at the surface, where organics formed under pressures and temperatures that would make our comet models blink. Gravity nudged it, then expelled it. For millions, perhaps billions, of years it drifted between suns, its surface sandblasted by micro-impacts, its interior locked in a cryogenic hush. All that time it was a question mark coasting. Now our star's radiation pours into its pores, down fractures, across ancient plains of frost. As the energy penetrates, bonds snap, molecules leap, and the coma inflates like a breath held too long and finally exhaled. The growing light teaches us as much about our ignorance as about the comet. Magnitude is not merely brightness. It is a ledger of thermodynamics. Each extra photon speaks of latent heat released, of sublimation fronts moving downwards, of clathrates cracking open. It hints at grain sizes lofted, at jets turning on and off as dawn marches across a rotating worldlet. If the nucleus is small, the same growth in coma demands ferocity. If larger, a gentler, broader exhalation suffices. We cannot yet disentangle the mask from the face. Hubble's constraints, kilometer scale but uncertain, tell us only that the coma overwhelms the core we need to see. The human response oscillates between mathematics and awe. We plot the light curve, we fit slopes and residuals. We compare to families of comets known by number and by temperament. The tame, the temperamental, the ones that flare like matchheads and the ones that smolder. Yet none of those were raised under another star. Astronomy is, at heart, comparative archaeology. We line up artifacts from different cultures of formation, our Oort cloud, another system's snowline, and we try to read the story the way an anthropologist reads a shard. In 3I/Atlas, the shard is still hot from the kiln. There is also the slower music that a documentary voice must not neglect. When sunlight surges into ancient ice, it is not only physics. It is time made visible. The coma's faint greenish breath, if it strengthens, will be the signature of molecules excited by ultraviolet light, electrons climbing and falling, emitting at narrow wavelengths like a neon sign in vacuum. Those photons have traveled for minutes from the sun, bounced off atoms that have traveled for eons through the dark, and then crossed millions of kilometers to enter a human instrument at a mountain's peak. Between emission and detection lies all of cosmic history's indifference and all of our curiosity's persistence. We are small, but we measure. We are late to the scene, but we listen carefully. Soon the observational window will narrow to a slit. Superior conjunction will force humility. The sun will insist on center stage. The comet will continue whatever metamorphosis it has begun, unseen by the species most hungry to witness it. If there is a lesson here, it is not only that the universe is complex, but that it cares nothing for our convenience. And so we plan and we hand the relay to Mars, and we wait for the geometry to turn favorable again. When it does, we may find a survivor burnished and reconfigured by heat, or a family of fragments fanning along the trajectory like sparks from a stone struck hard. For now, we attend to the present tense. Rising magnitudes, thickening air around a worldlet, an interstellar riddle entering the light. The numbers contradict our expectations, and that contradiction is the most faithful compass we have. Follow where it points, because 3I/Atlas is not only brightening, it is rewriting the quiet margin notes of our models into boldface. The universe has placed a messenger on our doorstep. We have only a little time to read what it carries. The story of 3I/Atlas did not begin with its eerie green glow or its swelling atmosphere. It began, as so many modern astronomical discoveries do, with the silent vigilance of robotic eyes. On a mountain in Chile, where the dry air of the Atacama Desert offers skies of unmatched clarity, the asteroid terrestrial impact last alert system Atlas was sweeping the heavens. On July 1, 2025, its instruments caught a faint, moving smear among the fixed stars. At first, it seemed an unremarkable entry into the endless catalog of small solar system bodies. Yet in that humble smudge lay the seeds of one of the greatest mysteries of modern astronomy. At first, the algorithms filed it away as just another minor body. Dim, slow-moving, inconspicuous. But follow-up images revealed a subtle haze. A coma, faint but unmistakable, cloaking a nucleus too small to resolve directly. The presence of a coma so far from the Sun was itself a revelation. This was no simple rock, but a volatile rich wanderer, already exhaling gases at distances where most comets remain frozen in silence. Digging into archival images, astronomers found traces of it stretching back weeks. The object had been hiding in plain sight, an unnoticed stranger until its true significance was recognized. Soon orbital mathematics made the truth undeniable. Its trajectory was hyperbolic, not an ellipse that would swing it back someday. Not even a stretched parabola that might keep it barely tethered to the Sun. Hyperbolic means one thing: escape. Too much velocity to be bound, too much momentum to be captured. Once its arc around the Sun is complete, it will leave forever, never to return. That was the signature of an interstellar visitor. The designation 3I followed, marking it as only the third confirmed body from another star system, after Oumuamua in 2017 and Borisov in 2019. These rare emissaries each rewrote the rules. Oumuamua was elongated like no asteroid ever seen, and its unexplained acceleration still stirs debates about exotic physics or subtle outgassing. Borisov seemed more familiar, with a coma and tail like a conventional comet, yet its chemistry, carbon monoxide in extraordinary abundance, betrayed an origin in conditions unlike our own. Now, 3I/Atlas adds its voice to this growing choir of strangeness. And once again the song is in a new key. Measurements of its nucleus remain frustratingly uncertain. Hubble's gaze suggested anywhere from 0.3 to 5.6 kilometers across, a margin wide enough to change the object's estimated mass by orders of magnitude. The difficulty lies in the glare of the coma, which wraps the nucleus in veils of dust and gas, hiding its true scale. What we can measure, however, is speed. As it hurtles inward, 3I/Atlas tears across the solar system at 130,000 miles per hour, faster than any native comet or asteroid. Solar gravity will only accelerate it further, perhaps to 150,000 miles per hour by perihelion. Earth itself orbits sedately by comparison at 67,000 miles per hour. No local body could attain such velocity unaided. 3I/Atlas carries the dynamical imprint of its long voyage between stars, accelerated by encounters with unseen giants, sculpted by the slow churn of the Milky Way's gravitational fields. Its discovery is a reminder of how easily such visitors could slip by unnoticed. Only the right instruments, the right algorithms, and the relentless scanning of the skies made it possible. The faint streak recorded that July night was nearly lost in the static of thousands of asteroids, comets, and fragments orbiting our Sun. But fate, or persistence, plucked it out, and suddenly humanity had a front-row seat to a story billions of years in the making. As larger observatories turned their gaze upon it, complexity unfolded. The Hubble Space Telescope captured its delicate coma and hinted at jets of gas fanning outward. The Very Large Telescope in Chile refined its measurements, while other instruments sought the spectral fingerprints of its composition. Early signs suggested carbon dioxide as a dominant volatile, unlike the water-rich comets of our own system. If true, that points to a nursery colder than ours, where CO2 could freeze readily while water remained vapor. Perhaps this object was born at the far edge of a foreign solar system, beyond a carbon dioxide snow line that shaped its destiny. Each observation, each data point, underscored a sobering truth. Our models, tuned to local bodies, may be inadequate. These are not our comets. They carry recipes from alien kitchens. Their proportions of ices and dust, their rotations and structures, are dictated by other suns, other disks of formation, other chemical balances. The galaxy's diversity is written in their cores, and each one is a sample delivered to our doorstep. There is, too, a philosophical undertone. These are not random stones, but remnants of creation itself. Each interstellar traveler is an artifact from a planetary nursery light years away. They are the fossils of other worlds that may have formed planets, moons, or even oceans. What froze into 3I/Atlas's nucleus might have been the same chemistry that, under different circumstances, would give rise to biology elsewhere. Now the sun's fire awakens it, and we, by chance, bear witness. Oumuamua gave us questions. Borisov gave us chemical anomalies. 3I/Atlas promises both, questions that will shake assumptions, and anomalies that demand new models. Already, its coma expands beyond expectations, its brightness climbs, its structure confounds. Already, its hyperbolic course teaches us about the dynamics of ejection from alien star systems. And still, the comet remains far from the sun, with the true drama yet to unfold. As astronomers prepared for its passage near Mars in October, anticipation mixed with urgency. Earth's own view would be curtailed by solar glare. Our hope lay in robotic companions circling the red planet, whose cameras and spectrometers might record what we could not. For the first time, we would not only have telescopes on Earth and in Earth orbit, we would enlist another world's sentinels to help us decipher a messenger from beyond. The stage was set. The question was not only what 3I/Atlas is, but what it will become under the sun's relentless gaze. Will it remain intact, or fracture like glass? Will it reveal compositions never before seen, or echo the patterns of Borisov and Oumuamua with a new twist? In every answer lies another question, and in each question, a reminder. The cosmos is wider, stranger, and older than any single system. This is the legacy of 3I/Atlas, an interstellar visitor that challenges us not merely to measure, but to rethink. Time is the heartbeat of astronomy, and for 3I/Atlas, the rhythm has grown urgent. Orbital mechanics, those precise equations indifferent to wonder, lay out a roadmap that we can neither delay nor accelerate. Each date is a doorway, and once it passes, it closes forever. We have only one chance to step through. The first great milestone falls on October 3, 2025. On that day, 3I/Atlas will glide past Mars at a distance of about 30 million kilometers. In cosmic terms, this is astonishingly close, well within the observational reach of the spacecraft that have long studied the Martian atmosphere and surface. For astronomers, it is an almost poetic coincidence. As Earth's view fades into the blinding presence of the sun, Mars takes up the mantle of watcher. Red planet orbiters, built to survey canyons and clouds, must now turn their lenses outward to catch a visitor from another star. Yet this moment of opportunity comes with irony. The very geometry that grants Mars a privileged view robs Earth of hers. As 3I/Atlas makes its closest pass by the red planet, the comet's position in our skies sinks deeper into the sun's glare. From mountaintop observatories and backyards alike, telescopes will strain against daylight scattering, until eventually the object slips beneath thresholds of detectability. The cosmos often gives with one hand while taking with the other. By late October, the climax approaches. On the 29th or 30th, the comet will reach perihelion, its nearest point to the sun, just 1.36 to 1.4 astronomical units. That puts it slightly closer than Mars's average orbit, within a realm of sunlight fierce enough to transform frozen interiors into fountains of gas and dust. But it is also the moment when Earth is most blind. The elongation angle, the separation between the comet and the sun in our sky, shrinks to fewer than 20 degrees. It is like trying to discern a candle's flame while staring straight into a spotlight. Even our most advanced telescopes cannot separate its faint signal from the star's overwhelming brilliance. And yet, the physics at play during this hidden interval are immense. Traveling at nearly 68 kilometers per second, more than twice Earth's orbital speed, 3I/Atlas will endure a blast furnace of radiation. Volatile compounds, long stable in interstellar night, may erupt in violent jets. Dust tails may lengthen, split, or even invert. Fragmentation is not just possible, but plausible. Many comets fall apart when they approach the sun too closely. Will this alien nucleus hold? Or will it shatter, scattering shards across its trajectory like sparks from a celestial anvil? We may not know until weeks later, when Earth regains its view. What makes this passage more than just a curiosity is its uniqueness. Periodic comets give us multiple apparitions. They return, and we refine our models over centuries. But interstellar objects are one-way travelers. Once gone, they are gone for good. 3I/Atlas will never circle back. Every hour we fail to observe is an hour of knowledge lost forever, knowledge about chemistry and physics that unfolded around another star billions of years ago. This is not simply a comet. It is a sample return mission launched by nature herself, dropped into our solar system by chance, and now vanishing into the night. The mathematics sketch not just a story of speed, but of energy accumulated over unimaginable distances. The comet's hyperbolic path tells us it was expelled from its birth system with vigor, perhaps slingshot by a giant planet, perhaps nudged by close stellar encounters. Every kilometer per second of excess velocity encodes the gravitational fingerprints of countless stars, dust clouds, and galactic tides it encountered along the way. By measuring its motion, we are reading a palimpsest of the Milky Way's dynamical history. As it departs perihelion, its velocity will diminish, not increase. The sun's pull that accelerates it inward will act as a brake on its outward journey. But it will never be enough to capture. Once free of our star, it will continue to coast into the interstellar gulf, carrying with it the secrets it revealed, and those we missed, during this fleeting intersection. Safety is, and has always been, a human concern, but here the mathematics grant comfort. The object never approaches Earth closer than $1.80, nearly twice our distance from the Sun. There is no risk, no shadow of collision. And yet, the curiosity feels more profound than any threat would. The true weight of this story is not fear, but opportunity. What we can learn about worlds we cannot visit, what we can glimpse of chemical processes that predate humanity, what whispers of alien star systems might be carried in its gases and dust. Even in absence, we will seek to learn. During conjunction, when our planet's vantage is denied, orbiters around Mars and perhaps even distant probes like BepiColombo or Parker Solar Probe may gather fragments of data. Not the continuous monitoring we crave, but enough, perhaps, to piece together the puzzle. When Earth's telescopes return to the hunt in November, the comet may be transformed, brighter, dimmer, fractured, or simply altered in ways we could not have predicted. What reappears may barely resemble what disappeared. This is the cruel generosity of orbital mechanics. It grants us certainty of times and places, but no promise of revelations. The comet will pass where the equations say it will, and the dates are written in celestial stone. But what it does as it passes, that remains the realm of mystery. It may teach us new chemistry, challenge the bedrock of comet physics, or dissolve into obscurity. The schedule is fixed. Our understanding is not. In this lies the beauty of astronomy, the knowledge that even with centuries of accumulated wisdom, the universe retains its ability to surprise. 3I/Atlas, hurtling faster than anything bound to the sun, is a reminder that we are part of a galaxy alive with motion, with collisions and expulsions, with stories that began light years away and find their epilogue here. If the trajectory of 3I/Atlas sketches its destiny, then its coma, the ghostly envelope of gas and dust inflating around its nucleus, reveals its present transformation. And this transformation defies precedent. By September 2025, NASA's SPHEREx telescope measured a carbon dioxide-dominated coma swelling to an extent almost inconceivable, roughly 348,000 kilometers across. To imagine this, place the sun at the center of a transparent bubble, then let that bubble grow until it stretches halfway to Mercury's orbit. That is the scale of the atmosphere now surrounding this alien traveler. A comet's coma often grows immense, yes, but this is a cathedral of vapor dwarfing the norms of cometary science. What drives such expansion? The answer lies in sublimation, the explosive leap of ice to vapor when heated by solar radiation. Unlike the melting of terrestrial snow, in vacuum there is no liquid interlude. Molecules vault straight from crystal to gas, carrying dust and grit with them. These liberated particles scatter light, making the coma luminous from millions of kilometers away. But size is only part of the mystery. What most startled researchers was composition. On Earth and in our system's comets, water is king. It is H2O that drives the activity, with carbon dioxide a secondary player. But 3I/Atlas inverts this balance. CO2 dominates. This suggests birth in a place colder than where our comets formed. Perhaps the deep frost zones of another star's disk, where carbon dioxide could freeze while water remained as vapor. The signature is alien, a chemical fingerprint from a nursery beyond our own. Yet even stranger than size or composition is geometry. A comet's tail, driven by sunlight, should stream away from the star like hair in a breeze. 3I/Atlas, however, presents what astronomers term an anti-tail, a plume of dust and gas extending sunward, toward rather than away from the sun. Hubble in July captured this peculiar forward-facing fan. Gemini South in August confirmed its persistence. This is no passing illusion. Something fundamental is happening. Conventional comet physics insists that solar photons push material outward, never inward. To see otherwise is to watch a rule unravel. Possible explanations strain the limits of our models. Perhaps large dust grains, too massive for photon pressure to sweep aside, were hurled sunward with sufficient velocity to maintain their course. Or maybe perspective deceives us. Earth's vantage point aligns with three-dimensional ejection angles in a way that projects a plume toward the sun. But these solutions feel partial. The anti-tail stability and definition suggest something more. Maybe an unusual rotation state with jets aligned in ways unknown among local comets. Maybe surface layers enriched with volatiles that ignite asymmetrically. Or perhaps plasma interactions, electrically charged dust dancing under the influence of the solar wind, are sculpting the geometry. The coma is not a static halo but a dynamic organism, alive with jets, fans, and filaments. Spectroscopy reveals gas velocities higher than expected, hinting at supervolatiles, substances that remained frozen only in the coldest interstellar conditions, now sublimating furiously when confronted with sunlight. Infrared measurements show temperatures inconsistent with solar heating alone. Could chemical reactions within the coma be releasing additional energy? Or are exotic crystalline structures, formed under pressures of a different system, collapsing as they warm, releasing latent heat? Dust itself offers clues. Analyses suggest an abundance of larger grains, precisely the sort required to maintain the anti-tail structure. Such grains might reflect a higher dust-to-ice ratio, or processing during interstellar drift that altered their resilience. If true, then this comet is not just chemically unusual, it is physically built in ways foreign to us. Consider the asymmetry of outgassing. Rather than a smooth, spherical exhalation, 3I/Atlas appears to vent in localized jets. These fountains, sprouting from discrete fractures or volatile-rich patches, may preserve the architecture of its formation environment. Scars from impacts long ago, or seams where interstellar heating cycles deposited or stripped material. Each jet is a voice speaking of history, telling us of collisions endured and eons traversed. The sheer expansion of the coma presents another puzzle. Models that work well for our comets falter here. Predictions must be recalibrated on the fly. Researchers adjust equations, input new ratios, stretch parameters, and still the data races ahead, demanding fresh frameworks. Science here is not neat but urgent, an improvisation on the edge of knowledge. Every observation is a clue, every anomaly a summons to rethink. And yet, beyond equations, there is awe. Imagine standing on a Martian plateau in early October, looking up, invisible to human eyes, yet there above you drifts an atmosphere larger than any planet, a gossamer sphere reflecting greenish light, exhaling chemicals older than our sun. Imagine knowing that the molecules glowing faintly in that coma formed around another star, in a nursery of dust and fire far across the Milky Way, and that you are witnessing their release after billions of years of silence. 3I/Atlas is not simply behaving differently. It is behaving impossibly by the rules we know. The coma does not just expand. It proclaims. Its tail does not simply stream. It confounds. Every measurement is both a discovery and a rebuke. We do not yet know enough. And perhaps that is the truest message of this alien emissary, that the galaxy harbors more ways of being a comet than our narrow experience has allowed us to imagine. In mid-September 2025, as if one surprise were not enough, 3I/Atlas underwent a transformation that startled even those already accustomed to its anomalies. The comet turned green. Not gradually, not as a faint tint detectable only by sensitive instruments, but in vivid fashion. A sudden emerald glow enveloping its coma and transforming its appearance in images captured worldwide. Against the velvet backdrop of space, it seemed almost alive, like a bioluminescent creature awakening in the deep ocean. The shift was most striking on the night of September 14th, during a lunar eclipse. With Earth's shadow dimming the glare of the moon, telescopes recorded a halo unmistakably infused with green. For centuries, comets have inspired dread and awe, their colors and tails woven into myth. But here was no superstition, this was molecular physics made visible. The culprit is likely diatomic carbon, C2, two carbon atoms bound together, energized by ultraviolet sunlight. In space, such molecules act like neon signs. When struck by photons, their electrons leap to higher energy states, then fall back, releasing light in precise wavelengths near 516 nanometers. The emerald glow of cometary folklore. Many comets near Earth display this hue, but in 3I/Atlas the story is stranger. For early spectroscopy had shown little carbon chemistry in its mix. Instead, carbon dioxide seemed dominant, with water and trace compounds in secondary roles. If C2 is the source, where did it come from? One theory suggests hidden reservoirs. As the comet crossed the 2AU mark in early September, sunlight may have penetrated to deeper pockets of carbon-bearing ices, long dormant, now suddenly exposed. Sublimation could have freed these molecules, or produced precursors that broke apart in ultraviolet light, releasing the C2 responsible for the glow. Another possibility is chemical alchemy inside the coma itself. Solar radiation dissociating CO2 and CO, then recombining fragments into unstable molecules that fluoresce green. Such pathways are poorly understood, for they require conditions rarely available in laboratory experiments. The mystery deepens when we examine the glow's unevenness. Images reveal patches where the green is stronger, regions of the coma with higher concentrations of carbon species. This suggests jets, fountains of gas and dust carrying particular chemistries, erupting from discrete areas on the nucleus. Like volcanic vents, each jet may expose a slightly different layer of history, releasing compounds preserved in pockets since the comet's birth. To map these variations is to read a geological diary written across light years. Color in astronomy is never just beauty. It is diagnosis. Green reveals energy transfer, collision rates, density distributions. By studying its intensity and spread, researchers reconstruct the three-dimensional structure of the coma. Early analyses indicate that the glowing carbon molecules achieve thermal equilibrium with surrounding gases, meaning they are intimately mixed into the flow, colliding and sharing heat. This provides a glimpse into the physics of how alien molecules interact when suddenly set free after billions of years in deep freeze. Comparisons sharpen our sense of wonder. Oumuamua showed no glow at all. Indeed, it displayed no coma, behaving more like a tumbling shard than a comet. Borisov exhibited more conventional colors, whitish blues from reflected light and familiar emission lines. But 3I/Atlas is the first interstellar comet to wear the emerald cloak so strongly associated with periodic comets of our own system. And yet even here it may be subtly different. Spectra suggest slight shifts, perhaps reflecting molecules unfamiliar to us, or at least in unusual ratios. If confirmed, this would mean that the green we see is not merely an echo of familiar chemistry, but a new dialect in the language of light. As Earth prepares to lose sight of the comet during superior conjunction, urgency mounts. Each night of observation is precious, each spectrograph recording a fleeting moment before the curtain of solar glare descends. Astronomers scramble to capture as much data as possible. High-resolution spectra to dissect the glow, time-lapse sequences to trace its changes, photometry to track its brightness. But time is short. By October, the green may intensify or vanish. By perihelion, unseen by us, it could blossom into radiance, or fade into ash-gray silence. There is a philosophical resonance to this color change. For billions of years, molecules of carbon lay dormant inside a frozen body wandering the galaxy. They endured cosmic rays, collisions with dust, magnetic fields, and the empty dark. Then, in a matter of days, under a sun it had never known, those molecules began to sing in visible light, sending emerald photons outward to cross millions of kilometers and strike the detectors of human instruments. In those photons lies the story of alien chemistry awakening for the first time since its birth. When we gaze at 3I/Atlas's green glow, we are not just seeing a comet. We are seeing time undone. Chemistry from another system, preserved across eons, now blooming into light before our eyes. It is a reminder that the universe is not static, but filled with dormant processes awaiting the right spark. And when that spark arrives, the result can be breathtaking. A messenger from beyond transformed into a beacon in emerald fire. The universe has a way of testing both our patience and our ingenuity. Just as 3I/Atlas begins to reveal its most dramatic secrets, the swelling coma, the impossible sunward plume, the eerie emerald glow, geometry conspires against us. The comet slides ever closer to the sun in our skies, and with it, observation becomes less and less possible. This is the tyranny of superior conjunction. When a target drifts too near our star's overwhelming brilliance, it effectively vanishes from earthbound eyes. No telescope, no matter how vast, can separate the faint whisper of a comet's light from the blinding flood of the sun. Even the giants of space-based astronomy face limits. The James Webb Space Telescope, perched far from Earth in the cold shadow of the L2 point, caught a rare spectroscopic glimpse of 3I/Atlas in August 2025. Its near-infrared spectrograph teased out the fingerprints of carbon dioxide, water, and trace organics. Hubble, in July, had captured the strange fan of dust pointing toward the sun. But these windows were narrow. By late August and September, both observatories had to retreat. Their safety systems forbid them from aiming too near the sun's disk, lest billion-dollar mirrors suffer catastrophic damage. At the very moment of maximum intrigue, the shutters must close. Ground-based astronomers are no less frustrated. They track the comet with persistence, feeding data to the Comet Observation Database, plotting light curves as points steadily climb above predicted values. But as September yields to October, the comet sinks closer to the horizon, where atmospheric scattering and the sun's glare bleach out its signal. Below 30 degrees of separation, even the most powerful telescopes struggle. Below 20 degrees, the game is lost. Imagine trying to see a candle flame fluttering beside a searchlight. That is the observational reality. The irony could not be greater. Models predict that late October, during perihelion, should be the most active period of the comet's life. Outgassing will peak, volatile ices will roar into space, and structural changes, fragmentation, tail formation, jets, are most likely to occur. Yet this exact period coincides with the curtain of invisibility. Our eyes on Earth will be blind while the comet undergoes its most spectacular transformations. It is as if the cosmos delights in staging its grandest dramas behind drawn blinds. Still, astronomy is nothing if not adaptive. Data continues to flow, patchy but invaluable. Amateur observers armed with modest telescopes contribute night after night, filling in gaps when major observatories are clouded out. Their measurements may wobble with noise, their calibrations less precise, yet collectively they trace the same unsettling story. Brightness surging faster than theory allows. Professional astronomers sift through the scatter, weighing uncertainties against the stubborn persistence of the trend. Is the comet truly brightening beyond prediction? Or are we fooled by systematic errors, by the chaos of measurement at the edge of detectability? The answer matters, for it distinguishes anomaly from illusion. Spectroscopy presents its own hurdles. To dissect a comet's light into wavelengths is to open a chemical diary, but such analysis demands brightness and clarity. As 3I/Atlas dims into the glare, spectral signals thin, drown in atmospheric scattering, and vanish into noise. Key wavelengths, especially in the ultraviolet, are most affected. This is cruel fate, for those very bands reveal the fragile molecules, cyanides, carbon chains, organics, that might most clearly announce alien chemistry. Each day of shrinking elongation is another page torn from a book we long to read. The challenge is not only observational but interpretive. Variations in brightness may reflect true volatility, bursts of gas erupting from fresh fissures, or maybe artifacts of differing filters, calibration mismatches, or atmospheric turbulence. With no baseline history of interstellar comets to compare, we cannot easily judge. Local comets return, allowing their quirks to be studied and modeled over decades. But 3I/Atlas is one time only, a guest passing swiftly through, offering no second chance. Every lost observation is irrecoverable, and so the burden shifts outward beyond Earth. Mars orbiters, never designed for such work, are hurriedly reprogrammed to attempt observations during the October 3rd flyby. Instruments built to scan Martian terrain or sniff its thin atmosphere may soon try to capture the faint glow of an interstellar wanderer instead. Later, perhaps Bepi Colombo on its way to Mercury, or Parker Solar Probe in its tight loops near the Sun, may catch fragments of data. None of these spacecraft were created for comet science, yet they may become our only eyes when the curtain falls. The situation exposes a deeper truth about science. Knowledge is always provisional, always partial. Nature sets the schedule, not us. We are accustomed to grand surveys and continuous monitoring, but here, at the mercy of orbital geometry, we are reminded of our limits. There are places we cannot see, moments we cannot witness. 3I/Atlas will live through its most intense encounter with the Sun largely unobserved by the species most eager to understand it. What emerges afterward may be dazzling or diminished, but it will not be the whole story. Perhaps that is fitting. For astronomy has always been a dialogue with absence, a science built on the traces of what we cannot touch directly. We look for signals in the noise, light in the glare, whispers in the silence. And sometimes what is most valuable is not the completeness of our knowledge, but the recognition of how much remains unknown. In a few weeks, 3I/Atlas will slip behind the Sun's veil. When it returns to our view, it will not be the same. It may be brighter, fractured, trailing filaments of debris. Or it may be dimmer, exhausted, fading back into anonymity as it departs our system. We cannot know. For now, we are left with questions, and the promise that mystery itself is part of the gift. As the comet drew closer to its October rendezvous with Mars, the focus of scientific hope shifted outward, away from Earth. While terrestrial telescopes prepared reluctantly for their enforced silence, engineers and astronomers looked toward the small flotilla of machines circling the red planet. Could these orbiters, designed for geology, atmosphere, and surface mapping, be repurposed, however briefly, into comet observatories? The answer, cautiously, was yes. Mars Express, Europe's veteran spacecraft launched in 2003, still carries cameras and spectrometers sensitive enough to detect faint targets. The Trace Gas Orbiter, part of ESA's ExoMars program, was built to sniff methane and other atmospheric molecules. Now, researchers scrambled to see if its instruments might instead taste the chemistry of an alien comet. NASA's Mars Reconnaissance Orbiter, famous for its high-resolution images of canyons and dunes, could pivot to track a speck of light racing through the stars. MAVEN, designed to probe Mars's upper atmosphere and its interaction with the solar wind, could in theory sense how that same solar wind interacted with 3I/Atlas's coma and tail. But the challenges were immense. None of these spacecraft were built to chase fast-moving objects. Their pointing systems are tuned for a planet, a massive nearby target filling the field of view, not a dim wanderer slipping across the starfield at interstellar velocities. Engineers needed to reconfigure tracking protocols, teaching the spacecraft to lock onto something far smaller and fainter than their original design anticipated. Signal strength was another hurdle. Even at closest approach, 3I/Atlas would be faint, magnitude 12 to 14, barely above the detection thresholds of most orbiter cameras. On Earth, such brightness would be well within the reach of amateur telescopes, but instruments on Mars are not optimized for faint, distant objects. They are built for landscapes, for weather, for planetary science. To glimpse the comet at all might require long exposures, careful scheduling, and perhaps a measure of luck. Dr. Wilson, one of the astronomers coordinating international efforts, acknowledged these limits openly. Observations were theoretically possible, but success would depend on a delicate balance. The comet's brightness at closest approach, the geometry of Mars's orbit, and the spacecraft's ability to interrupt their normal duties long enough to point outward. And all this had to be woven into already crowded timetables, communication windows with Earth, routine planetary science, maintenance activities. Yet the prize was extraordinary. From Mars's vantage point, the geometry of the encounter would differ dramatically from Earth's. The solar phase angles, the angle between Sun, comet, and observer, would be unique. Structures invisible from Earth could be revealed from Mars. The unusual anti-tail, for example, might appear from this perspective not as a sunward plume but as a three-dimensional feature, clarifying whether it is a genuine stream of dust or merely a projection trick. Even more enticing were the possibilities of plasma science. MAVEN, with its magnetometers and particle detectors, might catch the interaction of 3I/Atlas with the solar wind, a torrent of charged particles streaming from the sun. As this gale collides with the comet's coma, magnetic fields twist, shock fronts form, and ions accelerate. From such data, scientists could infer properties of the comet's interior, its composition, its porosity, even its hidden structure. In essence, the solar wind itself could become a probe and Mars a listening post. The coordination effort was unprecedented. NASA, ESA, and other agencies were forced to align schedules, share data pipelines, and develop observation plans across continents and time zones. The European Space Operations Center in Germany and NASA's Jet Propulsion Laboratory in California became hubs of communication, trading telemetry, calibrations, and observation scripts. Never before had orbiters around another planet been repurposed on such short notice to chase an interstellar comet. Yet obstacles loomed. Bandwidth from Mars to Earth is limited, and every image or spectrum of 3I/Atlas must compete with terabytes of routine planetary science data. Even if the spacecraft succeeded in capturing precious images, transmission delays might stretch into weeks or months. The comet would have already moved on by the time humanity saw the results. But success, even partial, would be transformative. A handful of images might pin down the nucleus's size and shape more precisely than Earth-based telescopes ever could. A few spectra might reveal exotic molecules invisible from our atmosphere. Plasma readings might uncover how alien chemistry responds to solar storms. Each dataset, however small, would be a treasure. And if fortune truly favored us, Mars orbiters might witness events Earth could not. Sudden outbursts, the development of jets, perhaps even the fracture of the nucleus itself. For as Earth entered its period of enforced blindness, Mars would remain humanity's only eye. The stakes were high. As terrestrial telescopes prepared to fall silent, the question loomed, would our machines on Mars rise to the challenge? Or would the interstellar visitor slip through our grasp, its most dramatic transformations unfolding unseen, unrecorded, unremembered except as speculation? In those tense weeks of planning, the comet seemed almost to mock us, dazzling in ways we could scarcely explain, then gliding toward a period when explanation would be most impossible. It was as though the universe were reminding us of our limits, daring us to reach farther, to improvise with what tools we had, to prove that curiosity could keep pace with chance. The promise of Mars-based observations was not just their novelty, but their vantage point. From Earth, by early October, 3I/Atlas would sink into the sun's glare, its position in the sky too perilous for most telescopes to attempt. But from Mars, the geometry was different. The red planet's orbital position offered a cleaner angle, a line of sight free from Earth's imposed blindness. For perhaps the first time in history, humanity's machines on another world would serve as our surrogate eyes, watching a cosmic event invisible from home. The advantages were striking. Solar phase angles, the relative positions of sun, comet, and observer, would be markedly different from the terrestrial view. Subtle features in the coma and tails, obscured by glare or projection effects from Earth, could stand out clearly from Mars. Researchers speculated that the peculiar anti-tail might resolve itself under these conditions. Was it truly a plume of dust hurled sunward, or merely an optical illusion caused by alignment? From Mars, the answer might emerge. Equally tantalizing were the possibilities of plasma science. As the solar wind washed over the comet's coma, the charged particles would set off electromagnetic fireworks. Bow shocks, induced magnetic fields, and ion tails stretching across millions of kilometers. MAVEN, with its sensitive instruments for measuring plasma and magnetic fields, might catch this interplay in exquisite detail. If successful, such measurements could reveal not only the comet's external activity, but also clues to its internal structure. Gas release rates, particle densities, and magnetic signatures might allow scientists to infer whether the nucleus was a loose rubble pile or a more solid monolith. Yet none of this came easily. Each orbiter operated on a strict timetable, juggling planetary science priorities with communication windows and maintenance sequences. Observation slots had to be carved out carefully, often at the expense of planned Mars studies. Instruments built for geology or atmospheric chemistry had to be reprogrammed to collect data on an interstellar comet. The trace gas orbiter, for instance, normally tuned to methane in Mars's skies, would attempt spectroscopy of faint alien molecules a world away. Mars Express, a veteran of nearly 2 decades, would shift from mapping surface minerals to capturing long exposures of a moving speck. The improvisation was both audacious and fragile. Communication bandwidth was another harsh constraint. Mars orbiters do not stream data freely. They transmit in bursts when planetary alignments allow, sharing limited channels with all their routine science. Each image or spectrum of 3I/Atlas would have to compete with gigabytes of atmospheric readings, surface maps, and engineering telemetry. Even if the spacecraft succeeded in capturing stunning data, humanity might not receive it until weeks later. The comet could already be past perihelion, transformed, or fragmented by the time its Martian portrait arrived on Earth. Despite these challenges, the international astronomical community pressed forward with unusual unity. Coordination calls spanned continents. The European Space Operations Center in Darmstadt collaborated with NASA's Jet Propulsion Laboratory in California. Data sharing agreements were expanded. Observation scripts were exchanged across agencies that had once guarded their priorities more jealously. For the first time, multiple planetary missions, each designed for wholly different purposes, were bent toward a single interstellar goal. What might they see? Hopes were modest but profound. Perhaps high-resolution imaging from Mars Express could resolve the nucleus itself, pinning down its elusive size and shape. Perhaps spectrographs could identify exotic volatiles invisible to Earth-based instruments, molecules that preserve the chemical fingerprints of another star's planetary nursery. Plasma data might show how alien chemistry collides with the solar wind, an experiment impossible to replicate in terrestrial laboratories. Even a handful of images and spectra could shift the conversation from speculation to evidence. But expectations were tempered. Reality reminded researchers that these spacecraft were never built for this task. At best, the outcome might be a few blurry frames, a handful of noisy spectra, a scatter of plasma readings. Yet even those scraps would be historic, humanity's first interplanetary collaboration to study an interstellar visitor. As October approached, the sense of suspense deepened. Earth was bracing for silence, its telescopes soon blinded by conjunction. Mars stood ready, a reluctant sentinel pressed into service. Would its orbiters succeed in capturing the secrets of 3I/Atlas? Or would the interstellar messenger slip past unseen, its brightest revelations hidden behind the veil of geometry and the limitations of human technology? Whatever the result, the effort itself marked a turning point. For the first time, humanity was orchestrating observations not just across continents, but across planets. Mars and Earth, bound by curiosity, worked in tandem to watch a visitor from beyond the stars. Success was uncertain. The attempt was inevitable. The comet's disappearance was inevitable, written into the mathematics of celestial mechanics long before its discovery. Superior conjunction, the alignment in which 3I/Atlas would appear perilously close to the Sun from Earth's vantage point, was no trick of chance. It was geometry uncompromising and absolute. As the comet curved deeper into the inner solar system, the angle between it and the blinding face of our star narrowed relentlessly. By early October, its solar elongation dropped below 30 degrees, crossing the threshold where even the most powerful ground-based observatories struggled to disentangle its faint light from the glare of daylight skies. For amateur astronomers, the loss came even sooner. Their telescopes, already straining against faint magnitudes, yielded only ghostly traces before surrendering to the flood of sunlight scattered through Earth's atmosphere. By mid-October, elongation slipped beneath 20 degrees. Even the great observatories, armed with adaptive optics, coronagraphs, and image processing algorithms, admitted defeat. 3I/Atlas faded not because it dimmed, but because the sun's brilliance overwhelmed it, erasing it from human eyes. This was not an abrupt vanishing, but a slow drowning. Night after night, observers reported weaker signals, fainter traces on photographic plates, noisier data points in their light curves. Then one evening, nothing. It was as though the interstellar wanderer had simply dissolved into daylight. For Earth, the window was closed. The most critical weeks of its passage, late October through early November, would unfold in secrecy, beyond the reach of our instruments. The irony was cruel. All indications suggested that this hidden period would mark the comet's greatest upheavals. The September surge in brightness, the vast carbon dioxide coma, the emerald glow, all implied processes building toward a climax at perihelion. Theorists warned of potential fragmentation, catastrophic outbursts, and chemical reactions never before observed. But when those revelations came, Earth would be blind. The universe had drawn a curtain at the very moment the drama reached its peak. Some hope lingered in spacecraft scattered across the solar system. SOHO, with its coronagraphs, had revealed dozens of sun-grazing comets over the decades. Yet 3I/Atlas's trajectory placed it too far from the solar limb to fall within SOHO's narrow view. Parker Solar Probe, flying daringly close to the sun, might brush through the comet's ion tail. But the probe's instruments were tuned for solar physics, not cometary science, and any detection would be incidental at best. Bepi-Colombo, en route to Mercury, held instruments capable of plasma and dust measurements, but its geometry relative to the comet was uncertain. Each possibility was tantalizing, yet unreliable. Astronomers did what they could. Computer models were refined, extrapolating from September's last reliable measurements. Simulations mapped scenarios. A quiet perihelion, a dramatic outburst, a shattering fragmentation. The models diverged wildly, underscoring how little was truly known. Without new data, even the most sophisticated predictions hovered between science and speculation. And so, for 4 to 5 weeks, silence. No images, no spectra, no light curves. Only the hum of theories and the restless patience of waiting. In classrooms, the comet story paused, leaving teachers with a cliffhanger. In observatories, instruments were turned to other targets, their operators counting days until solar elongation widened again. In public discourse, interest dimmed, as the lack of new images stilled the flow of headlines. The most photogenic phase of the comet's life, its perihelion transformation, would pass unseen. When 3I/Atlas reemerged in late November or December, it would be different. Every comet is altered by perihelion, but for this interstellar traveler, the change might be profound. Would it return as a single intact body, brighter and more volatile than before? Or as a fading wisp, its reserves spent in a hidden fury? Or perhaps as fragments, scattered shards tracing separate paths through the dark? Observers prepared for the challenge. After conjunction, the comet would appear in a new patch of sky, requiring fresh searches and recalibrated ephemerides. Telescopes would sweep patiently, reacquiring the faint signal of a body transformed. The object that reappeared might not even resemble the one that vanished, a reminder that the cosmos is under no obligation to maintain continuity for human observers. For now, though Earth was blind, the messenger from another star moved closer to its fiery test, and humanity could only imagine. Superior conjunction had taken it from us, delivering a lesson both humbling and eternal. No matter how advanced our instruments, we remain prisoners of perspective, bound to our planet's orbit, forced to accept the geometries written in the language of gravity. Deep within the glare of the sun, beyond the reach of every telescope on Earth, 3I/Atlas hurtled toward its moment of destiny. Perihelion, its closest passage to our star, was scheduled for October 29th to 30th, 2025. At just over 1.36 astronomical units from the sun, It would never approach the infernal proximity of so-called sun-grazing comets. Yet for this fragile interstellar traveler, such a distance promised a crucible of heat and radiation more intense than anything it had endured in millions, perhaps billions, of years of wandering through the cold void between stars. At perihelion, its velocity would crest at nearly 68 kilometers per second, 152,000 miles per hour, making Earth's steady orbital pace of 30 kilometers per second seem almost leisurely by comparison. That speed carried kinetic energy on a scale so vast it strained the imagination. The comet had acquired this momentum during a galactic journey shaped by countless stellar gravitational fields and the slow whirl of the Milky Way itself. In perihelion's furnace, that momentum would crash against the physics of solar heating, driving volatile materials to awaken in a frenzy of outgassing. The expectation was transformation. Water ice, carbon dioxide, carbon monoxide, and more exotic compounds buried in its interior would all begin to sublimate at once, turning frozen reservoirs into jets of gas that burst from the nucleus with violent force. The coma, already vast enough to rival planetary orbits, could expand to an even more staggering scale. Dust fountains might erupt, carving pillars thousands of kilometers long into the vacuum. The eerie sunward-pointing plume, the comet's confounding anti-tail, might intensify, reshaping itself into structures that defied conventional comet physics. But perihelion was also a test of survival. Cometary nuclei are fragile, bound together not by the strength of stone but by the loose cohesion of ice, dust, and porous voids. Thermal gradients could fracture the object as one side heated faster than the other. Pressure from trapped volatiles could rip it apart from within. The history of comets is littered with examples. Shoemaker, Levy 9, torn into fragments by Jupiter's tidal pull. Comet Ison, shredded near the Sun in 2013. Many wondered if 3I/Atlas would follow the same fate, scattering itself into a constellation of debris as its interstellar voyage ended in dissolution. Its unusual chemistry raised further questions. The dominance of carbon dioxide suggested perihelion activity unlike any solar system comet. CO2 sublimates more vigorously than water ice, potentially fueling explosive outbursts. If structural weaknesses existed, these might be enough to trigger catastrophic fragmentation. Yet the comet's hyperbolic trajectory meant it would sweep past perihelion quickly. Unlike slower, elliptical comets that linger near the Sun, 3I/Atlas would experience only a brief but intense exposure before racing outward again. Some theorists argued this brevity might spare it, allowing survival where other comets had perished. If it endured, it would not emerge unchanged. Spectral lines invisible before might flare to life as new chemical species sublimated. Organic compounds buried deep within could break down under ultraviolet light, creating cascades of fluorescent colors beyond the green glow already observed. The coma might shimmer with a spectrum of emissions, each a molecular fingerprint of alien chemistry awakened by the sun-plasma interactions would intensify as the solar wind streamed through the ionized gases, shaping electromagnetic tails that could stretch millions of kilometers into space. If it fragmented, however, the story would become even more extraordinary. Each shard of the nucleus would expose a fresh cross-section of primordial material, layers preserved since its birth around another star. To study those fragments would be to read, for the first time, the stratigraphy of an alien planetary nursery. Yet whether intact or broken, the comet would emerge altered, bearing scars of its passage through the Sun's radiation furnace. Astronomers, blind during the drama, could only wait. When the curtain lifted in November, the comet that reappeared might look nothing like the one that vanished. A brilliant survivor, a fading wraith, or a scatter of luminous fragments. Any outcome was possible. Perihelion was the climax of its story, and for now the stage was hidden from us, lit only by the fires of the sun and the forces of physics. To place 3I/Atlas in perspective, astronomers looked back at its rare predecessors. In the brief annals of interstellar visitors, only two objects had been confirmed before this, 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Each shattered expectations, each rewrote theories, and now 3I/Atlas added a third chapter, stranger still. Oumuamua was the first, Discovered by the Pan-STARRS telescope in Hawaii, it appeared at first to be a mundane asteroid, a faint streak of light moving too fast to be bound to the sun. But its properties quickly baffled researchers. It displayed no coma, no tail, nothing that resembled a comet. Yet as it sped away, it accelerated, as though pushed by some unseen force. Outgassing was proposed, but none was detected. Radiation pressure acting on a thin, elongated shape was another explanation, fueling speculation that spiraled far beyond science, into whispers of alien probes and technological artifacts. Whatever it was, Oumuamua was unlike anything observed before, a messenger that slipped from our skies as mysteriously as it appeared. 2 years later came 2I/Borisov, discovered not by a major observatory but by an amateur astronomer in Crimea. Borisov, by contrast, looked far more familiar. It developed a coma, grew tails, and behaved like a comet in almost every respect. Yet when its chemistry was analyzed, it told a new story. Carbon monoxide in unusually high abundance, more than in typical solar system comets. This hinted at a birthplace colder or chemically distinct from our own stellar nursery, perhaps at the frigid edge of another protoplanetary disk. Borisov was a comet that looked ordinary at first glance but proved alien in its details. Now 3I/Atlas stood alongside them, but it was no mere addition. It dwarfed its predecessors in mystery. Its coma expanded to half the diameter of the sun. Its brightness surged unpredictably. Its plume pointed not away from the sun, but toward it. And its chemistry leaned heavily on carbon dioxide, making it even more exotic than Borisov. If Oumuamua challenged our definitions of asteroids and comets, and if Borisov broadened our view of cometary chemistry, Atlas demanded entirely new frameworks. The comparisons deepened when considering size and speed. Oumuamua was perhaps 400 meters long at most, a shard rather than a world. Borisov's nucleus was larger, about 1 kilometer wide, consistent with familiar comets. Atlas, though, defied easy measurement. Estimates placed its nucleus somewhere between 0.3 and 5.6 kilometers, a range so broad it underscored how its vast coma obscured any clear view of its solid heart. But its speed was undeniable. With a hyperbolic excess velocity of nearly 39 kilometers per second, it carried more raw momentum than either of its forerunners, energy collected from a longer, more complex odyssey through the galaxy. Taken together, these three objects suggested a staggering truth. Interstellar visitors are not a rare breed of similar wanderers but a wildly diverse population, each shaped by the unique chemistry and physics of their home systems. One arrives as a silent shard, another as a familiar yet chemically alien comet, and the third as an enigma wrapped in green light and impossible geometry. The lesson was clear. The Milky Way is filled with possibilities far beyond the limited template of our solar system. 3I/Atlas also revealed how swiftly our capabilities had advanced. In 2017, Oumuamua came and went with only weeks of observation, leaving more questions than answers. By 2019, Borisov was caught earlier and analyzed with powerful instruments, yielding rich chemical data. By 2025, when Atlas appeared, humanity had an armada of tools: Hubble, James Webb, and soon the Vera Rubin Observatory, all ready to extract information that would have been impossible just a decade before. Still, conjunction and geometry mocked us, showing that even with advanced instruments, timing could still rob us of revelation. The arc of these three encounters traced the contours of a new science, one that had barely existed 10 years earlier. Interstellar object studies were once theoretical, limited to models and probabilities. Now they were an observational reality, each new visitor a data point in a growing catalog of galactic messengers. And each time, the lesson grew sharper. The galaxy's diversity is not an abstraction but a living fact, streaking into our skies, briefly visible before vanishing again into the dark. Where Oumuamua hinted at the strange, where Borisov revealed the subtle, Atlas delivered the spectacular. It was a cosmic reminder that we had only begun to understand the breadth of what drifts between the stars. And whatever secrets perihelion might hold, the comet had already cemented its place in the small but transformative history of interstellar wanderers. Science thrives on clarity, yet with 3I/Atlas clarity seemed always just out of reach. Every new observation raised as many questions as it answered, leaving astronomers circling around contradictions, puzzling over incomplete evidence, and debating in hushed tones what might truly be unfolding before their eyes. The comet was less a solved riddle than a detective story, with crucial pages torn from the book during its most critical chapters. The most fundamental dispute lay in the nucleus itself, its size, its shape, its very nature. Hubble's data hinted at something between 0.3 and 5.6 kilometers across, a range so wide it bordered on useless. Infrared modeling suggested a bright, reflective body, small but efficient at scattering sunlight. Optical measurements, however, implied something darker, larger, and heat-absorbent. Was it a compact monolith or a fragile rubble pile? The coma's immensity blurred the answer, drowning the solid body in a haze of gas and dust. Without a clear nucleus, calculations of density, surface area, and stability became little more than educated guesses. The chemistry only deepened the enigma. James Webb's infrared spectrograph spoke with unusual certainty. Carbon dioxide was the dominant volatile, outpacing water by wide margins. That in itself was a revelation. Solar system comets, almost without exception, are ruled by water. Yet this CO2 dominance clashed with other observations. The sudden green glow in September pointed to diatomic carbon, a molecule not easily explained by a carbon dioxide-rich environment. Some hypothesized that photodissociation, UV light breaking apart CO2 and CO, could spawn the necessary carbon fragments. Others suspected hidden reservoirs of organic molecules, awakened only when the comet crossed some critical thermal threshold. Ground-based instruments added yet more complexity. Cyanides, organics, and other faint molecules appeared in their spectra, hinting at a stew of chemistry richer than Webb's conclusions alone suggested. Was Atlas a simple CO2-rich comet, or was it a far more chemically diverse body, its volatile cocktails only beginning to reveal themselves? The contradiction was stark. Instruments agreed on some signatures, disagreed on others, and left no single coherent picture. Perhaps the strangest puzzle of all was the anti-tail. By every principle of physics, dust and gas should stream away from the sun under the pressure of radiation and solar wind. Yet Atlas's plume pointed back toward the very source of light and heat. Competing models tried to explain it. One invoked large dust grains, too massive for photons to push aside, launched sunward at high speeds. Another leaned on plasma physics. Charged particles in the coma interacting with magnetic fields to redirect flows in unexpected directions. Still others pointed to rotation. If the comet spun slowly enough, volatile outgassing could concentrate into sunward jets from persistently heated regions. Each theory held promise, yet none fully matched the persistence and definition of the plume observed. Even the comet's rotation remained a ghostly unknown. Light curve analysis, the standard method for detecting rotational periods, failed to find clear cycles. Was Atlas nearly spherical, spinning so slowly that variations went unnoticed? Or was it tumbling chaotically, its brightness dominated by volatile activity rather than shape? Without rotation data, models of its structural integrity and long-term stability floated unanchored. Then there was the question of brightness. September's surge was undeniable. Multiple networks confirmed it. But by how much? Some measurements claimed several magnitudes, others suggested modest gains. The scatter reflected both real variability and the difficulty of observing a faint, fast-changing object at the threshold of detectability. Was the brightening a dramatic outburst, or merely a heightened phase in a complex but natural cycle? With no baseline from previous returns, this being its only visit, comparisons were speculative. Origins remained equally uncertain. Traceback simulations suggested a birthplace somewhere in the thin disk of the Milky Way, the galaxy's vast star-forming plane. Yet the error margins grew enormous when extrapolated backward across millions of years. Did it emerge from a young, carbon-rich system? From a colder star where CO2 froze abundantly near its snow line? Or from a chaotic environment where ejection came early, locking alien chemistry into a frozen tomb? The answers lay buried in its nucleus, but geometry and distance kept them hidden. In many ways, 3I/Atlas became a mirror for the limits of science. Each measurement revealed not certainty but the boundaries of what could be known. Was it a single body or a cluster of fragments? Was its brightness surge a sign of fragility or vitality? Was its green glow evidence of simple chemistry or something unprecedented? For every hypothesis, counterpoints stood ready, each supported by fragments of data, none decisive. And so the comet hung in the balance, its secrets shielded by distance, glare, and time. The debates would rage until conjunction ended, and perhaps even after. For now, the scientific community held its breath, knowing that when Atlas reappeared, it might either resolve the contradictions or deepen them forever. Before daring to wander into realms of the extraordinary, science must first test every plausible explanation within the boundaries of known physics. For 3I/Atlas, the path toward understanding begins not with speculation about alien technology or exotic matter, but with the sober recognition that nature, even when strange, is seldom inexplicable. The comet may appear otherworldly, but its behavior could still be the product of processes already described by physics. Processes that until now have simply never been witnessed under such extreme conditions. The dominance of carbon dioxide in its coma provides the first major clue. In our solar system, comets typically form beyond the so-called snow line, where temperatures are low enough for water to freeze. Water ice thus becomes their primary volatile, with carbon dioxide and carbon monoxide playing secondary roles. But 3I/Atlas seems to invert this ratio, hinting at a birthplace where CO2 froze more readily than water. Perhaps it formed closer to a cooler, dimmer star than our Sun, where carbon dioxide condensed early while water vapor remained unstable. Or perhaps it emerged from a carbon-rich nebula, a protoplanetary disk with a chemistry weighted towards CO2. The strange balance of volatiles is less an impossibility than a fingerprint of an alien stellar nursery. This also helps explain its extraordinary outgassing. Carbon dioxide sublimates at lower temperatures than water, meaning it can begin erupting into gas long before water ice becomes active. That property may account for the September brightening and for the unprecedented size of its coma, which ballooned to nearly half the Sun's diameter. What seems alien might simply be the consequence of chemistry unfamiliar to us, shaped by a different stellar environment. But chemistry alone cannot explain everything. The anti-tail remains an unsolved challenge. Here, plasma physics enters the picture. When solar ultraviolet light ionizes the gases in a comet's coma, it transforms the space around the nucleus into a tenuous plasma. Charged dust grains suspended in this environment can interact with magnetic fields carried by the solar wind, creating patterns and flows more complex than simple radiation pressure models predict. In laboratory experiments, dusty plasmas have been observed to self-organize into filaments, arcs, and even spiraling structures. Transposed to the immense scale of 3I/Atlas, such interactions could produce a sunward-pointing plume, seemingly in defiance of the ordinary laws of cometary dynamics. Another possibility lies in rotation. If the nucleus spins slowly or irregularly, its day side may heat to extreme temperatures while its night side remains frigid. Such a temperature imbalance could focus outgassing into narrow, sun-facing jets, projecting material in the very direction theory says it should not go. And yet, because Atlas's rotation remains undetected, such ideas live in the realm of inference rather than proof. The green glow that swept across its coma in September may also yield to natural explanation. Green emissions are often associated with diatomic carbon, C2, which fluoresces when energized by solar ultraviolet light. But Atlas was not initially rich in the expected carbon-bearing molecules. How then did it glow? One answer is photodissociation. Ultraviolet radiation may have broken down carbon dioxide molecules, releasing carbon monoxide and free carbon atoms, which then combined into C2. Once the comet crossed a particular threshold of solar heating, near 2 astronomical units from the Sun, this cascade could have ignited, producing the emerald halo caught by telescopes. In this view, the glow was not a mystery, but the natural chemistry of alien volatiles meeting solar light for the first time. Other organic molecules may also play a role. Polycyclic aromatic hydrocarbons, amino acid precursors, or complex carbon chains could lurk within the nucleus in trace amounts. These compounds, once liberated, break apart under radiation into fragments that fluoresce at visible wavelengths, some of them green. If so, 3I/Atlas could be carrying the very same molecular building blocks that seeded planets and perhaps even life in other corners of the galaxy. This chemistry, while unusual, might be another variant of nature's cosmic experiments with carbon. The comet's internal structure must also be considered. A porous nucleus, riddled with voids, allows sunlight to penetrate deeper than in compact comets. This deeper heating could awaken subsurface volatiles suddenly, producing the rapid brightness surges that defy models calibrated to denser bodies. In addition, interstellar travel itself may have altered its structure. Bombardment by cosmic rays, impacts with dust grains, and thermal cycling through different interstellar environments could weaken or reshape its interior, priming it for unusual behavior once it entered our solar system. Taken together, these natural processes, CO2-rich composition, plasma interactions, unusual rotation, photodissociation cascades, organic chemistry, porosity, and interstellar weathering may explain much of what seems so alien about Atlas. Each is grounded in known physics. Each has precedent, if not in comets of our system, then in laboratory studies or theoretical models. But what makes Atlas extraordinary is how these processes converge, layered upon one another, producing effects never before seen in a single object. The comet's strangeness may not be proof of the unknown, but rather proof that nature, when viewed through the lens of galactic diversity, is stranger than our limited local experience has prepared us for. In this light, 3I/Atlas is not a violation of physics. It is physics revealed in its broader, more universal scope. Yet whenever nature presents phenomena that strain our explanations, the human imagination drifts toward more radical possibilities. History shows this well. Pulsars, first discovered as repeating radio signals, were nicknamed LGM for little green men before they were revealed as neutron stars. Fast radio bursts were once whispered about as alien beacons, only to be tied to exotic stellar processes. With 3I/Atlas, its bizarre characteristics, its swelling coma, its green luminescence, its impossible sunward plume, have inevitably provoked speculation that wanders beyond conventional astrophysics. One of the most persistent ideas is the alien technology hypothesis. Ever since Oumuamua's strange acceleration ignited debates about artificial sails or probes, the possibility hovers over every new interstellar visitor. Could Atlas be some dormant artifact, designed to awaken when bathed in the light of a foreign star? Its sudden brightening, its inexplicable plume, its evolving chemical displays. Might these be activation sequences rather than natural processes? Perhaps what we see as outgassing is controlled venting, or what we call an anti-tail is in truth a directed emission of energy or material carrying data across the void. But sober evidence resists the romance. The spectra reveal nothing exotic. No alloys, no signals, no anomalous isotopes. What emerges from Atlas's coma is carbon dioxide, dust, organics, materials as natural as ice and rock. If it is artificial, it is flawlessly disguised as the most ordinary matter. And science, guided by evidence, must treat it as natural until proven otherwise. Another speculative idea lies in the realm of living plasma. In laboratories, dusty plasmas, clouds of charged particles and grains, sometimes self-organize into patterns that appear startlingly lifelike. Spirals, waves, filaments, structures that mimic primitive forms of metabolism or reproduction. Could Atlas, in its immense coma, be generating such patterns on a cosmic scale? Could its glowing plasma envelope act like a quasi-living system, responding to solar radiation with emergent behaviors that mimic biology without being alive in the carbon-based sense? If true, such entities might drift between stars, dormant in the dark, awakening only near suns to reveal transient, ghostly lifelike patterns. More radical still is the scout hypothesis. Some imagine Atlas as a vessel of intent, a probe designed to reconnoiter star systems, programmed to activate in phases. Brightening, signaling, studying. Its approach near Mars, its perihelion passage, its emissions, all could be interpreted as part of an observation protocol. If so, its green glow might be a flare of sensors, its anti-tail a transmission beam. To think this way is to indulge in science fiction, but science fiction often reflects the longings and fears of its age. Others wander even further into theory. Exotic matter. Perhaps Atlas contains substances beyond the periodic table as we know it, or interacts with dark matter in ways our instruments cannot yet detect. Maybe the plume is shaped not by dust grains, but by interactions with physics unknown to us, quantum processes scaled to the macroscopic or gravitational anomalies we have yet to name. If true, the comet could be a natural laboratory of the cosmos, carrying hints of physics beyond the standard model. And then, at the edge of speculation, lies the temporal anomaly, that Atlas is not merely a wanderer from another star, but a messenger from another time. Could it be a shard of our own solar system, cast backward through time by some unknown mechanism, carrying secrets of a future we cannot yet imagine? To entertain this is to brush against paradox, but the idea lingers: what if this is not just a visitor but a reflection? Each of these theories rests on imagination more than data. None has observational evidence to stand on. Yet they persist because Atlas is unlike anything we have ever seen, and the human mind, when confronted with mystery, leaps beyond the safe walls of probability. In this sense, even speculation has value. It reminds us how vast our ignorance remains and how fragile our certainty can be. Still, history cautions humility. Pulsars, FRBs, cometary anomalies, all once seemed alien, all eventually yielded to natural explanations. Atlas, too, may prove nothing more than a comet, an extraordinary comet, yes, but still a comet. The true wonder may not be that it defies physics, but that physics itself, stretched into alien contexts, creates wonders more surprising than fiction. The clock is ticking. Every day brings 3I/Atlas closer to the decisive moments that will define its story, not only for astronomers, but for all who recognize the enormity of what it represents. A fragment of another star system, here and gone in a single sweep. This countdown is not one of danger but of opportunity. A race between celestial mechanics and human ingenuity to learn all that can be learned before the visitor slips forever back into the dark. The first milestone is October 3, 2025, the flyby of Mars. At a distance of roughly 30 million kilometers, this approach offers a window no Earth telescope can match. Orbiters circling the red planet will attempt to redirect their instruments, straining against their design limits to glimpse the comet's nucleus, resolve its structure, and taste its chemistry. It is an improvised campaign, fragile and uncertain, but perhaps the only chance to keep eyes on Atlas while Earth falls blind. Success could mean revelations, a precise nucleus size, direct images of the enigmatic plume, the detection of molecules invisible from Earth. Failure could mean silence, the comet passing by unnoticed, its secrets locked away as it heads toward the sun. The second milestone comes only weeks later. Perihelion, October 29th to 30th. Here lies the crucible. As the comet hurtles past at over 68 kilometers per second, it will endure the most intense solar heating of its long existence. Will it survive intact, shedding gas and dust in spectacular plumes? Will it fragment into a family of shards, scattering like embers through the inner solar system? Or will it fade quietly, its volatile reserves depleted in a hidden outburst we never witnessed? Whatever happens, it will happen largely unseen. Concealed by the overwhelming glare of the sun, perihelion is the story's climax, and humanity can only imagine the drama unfolding in those weeks of forced blindness. The third milestone is reemergence, expected in late November or early December. By then, Atlas will have transformed. It may shine brighter, with new tail structures unfurling across the sky. It may appear diminished, a pale wisp fading as quickly as it flared. Or it may be many objects, fragments of a once-whole nucleus, now tracing separate paths. Telescopes will search eagerly for its return, for whatever shape the interstellar messenger has become. In that moment, speculation will give way to revelation, and the debates that have filled the silence will be tested against reality. Beyond these near-term events, the comet's future encounters remain on the calendar of the cosmos. In March 2026, its trajectory will carry it into the outer solar system, skimming past Jupiter's domain. Though more distant than the Mars flyby, This passage could still provide a chance for spacecraft to glimpse it anew before it departs forever, flung outward on its hyperbolic course. After that, it will be gone, slipping into the interstellar night, not to return. The implications of what we learn or fail to learn will ripple far beyond this single object. Each interstellar visitor is a data point in a vast galactic puzzle, a direct sample of planetary formation processes scattered across the Milky Way. Already, 3I/Atlas has expanded our sense of the possible. A carbon dioxide-rich comet with a colossal coma, a sunward plume, and chemistry that hints at alien conditions. Its behavior challenges our models, reminding us that comets in our solar system are but one expression of a broader galactic diversity. Future discoveries will come. The Vera Rubin Observatory, soon to begin its legacy survey of space and time, promises to detect interstellar visitors with regularity. What is rare today, 3 confirmed objects in less than a decade, may soon become routine, a steady stream of messengers to study, compare, and classify. Missions like ESA's Comet Interceptor, waiting at the Earth-Sun Lagrange point for a yet unknown target, are designed to seize those opportunities, ready to chase the next object that wanders across the stars. But 3I/Atlas holds the mantle of the present, the here and now. It has already forced astronomers to question assumptions, to refine models, to consider plasma physics, chemistry, and geology in new ways. For the public, it has rekindled awe, the awareness that our solar system is not isolated, but porous, open to the drifting remnants of other suns. To look at Atlas, even through grainy images and data plots, is to see beyond the boundaries of our neighborhood, into the processes shaping worlds across the galaxy. As the countdown continues, the comet's legacy grows clearer. Whether it blazes, fragments, or fades, it has already changed the way we think about interstellar visitors. It has reminded us that the universe still holds mysteries vast enough to humble, to inspire, to ignite both science and imagination. In the end, Atlas is not merely an object. It is a messenger, a question, a glimpse of the galaxy's endless creativity. When its final light curves are plotted, when its data is archived, when its trajectory carries it beyond the reach of our instruments, one truth will remain. We were here to see it. We were alive in the brief moment when a wanderer from another sun passed through our skies, whispering of other worlds, other chemistries, other stories written in the dark between stars. And that is enough to remind us why we watch the heavens, not only for answers but for wonder.